Yes.
My screen?
Looks great.
Okay, great. And when I, oh, no, hang on. Just want to make sure that it's picking up the movement of slides. Have I gone to the next slide? No. How about now?
Yeah.
Fantastic. And you can't see my notes?
No.
Oh, brilliant. It's working. Okay, great. Thank you very much for that. And thank you for having me at...
So let me introduce you first, Brian.
Oh, sorry. Go ahead.
So our next speaker is Brian Fannin, who is a research actuary at the Casual Actuarial Society. Brian has over 20 years of actuarial experience. He's associate of the CAS, as well as the certified specialist in predictive analytics. He worked in a variety of roles in commercial insurance, both in US, Europe, London, and Asia. I think one of the key features for Brian is he's a R evangelist, and so he authored a book called R for Actuaries and Data Scientists with Applications to Insurance, published by Actex as well. He's teaching many workshops and seminars on R. He has been with CAS since 2018 as a research actuary, and his role is to support CAS committees and research partners in developing relevant and practical content. And that is also the theme of the talk today about tomorrow's actuary. Brian, great to have you, and the Zoom is all yours.
Great, thank you, and apologies for jumping the gun there. Very happy to be here today. Thanks for the opportunity. I was asked to present and was given no parameters about what it is that I would discuss, which is a kind of a challenge and an opportunity. I'll go on record as saying that I have not now, nor am I ever likely to develop an innovative actuarial technique like the one that Mario just shared with us. But that understood, I do love finding new ways to think about how we can bring technology to bear to solve actuarial problems. Technology is a sort of a forward-looking area of humanity. And so that leads me to this idea of what tomorrow's actuary would look like. So with no small amount of arrogance and or foolishness, I'm going to think about what the actuary of the future might encounter. First, though, I'm going to go into the past. Show of virtual hands or just sort of mental thought about who this person might be. I'll confess that had I not Googled the image, I would not have recognized this person. But this is Edmund Hallie, who is widely regarded as ceremonially the world's first actuary. He got his start, among the other things that he did, obviously he very famously studied comets, but one of the things that he did was he looked at some data from Breslau, Poland, about births and deaths, and came up with the world's first mortality table. And that analytical study of risk was the forerunner of modern actuarial practice. Now, why he did it is something that it might or might not have been to solve a practical problem. It could have been just him satisfying his own curiosity. But as it happens, this is quite useful. Great. So at that time, and for centuries prior to that, countries in Europe and elsewhere would go to war. When they do so, the monarchy would need to finance the combat, and this is quite expensive. The way that they would fund the expenditures often is that they would sell pensions. So let's say I'm the King of England, and I will I will tax my subjects, but if I want additional revenue, then I'll say, all right, for the rest of your life, I will pay you £1 per year until you die. There was not really any reconciliation between the revenue that came in and the future expenditures. But Hallie's work was something that was instrumental in coming to grips with, well, if we do want to raise revenue in the moment, how can we establish the pensions in such a way that we can continue to afford this? It's all well and good to have revenue today in order to finance wars, that does us very little good if after the dust has settled from combat, we're paying pensions at a rate that is faster than the revenue that we are receiving. So this is one of the first ways that we're coming to grips with a risk engineering, a risk financing problem that has an actuarial solution. Now, things have changed since Hallie's time, and let's talk a little bit about that. So let's talk about the technology that we can bring to bear. Hallie would have done all of his work on pen and paper. What is it that actuaries do? What technology do we bring to bear? So last summer, the CAS conducted the first of what we hope will be an annual survey of our members and people who are sitting for CAS exams, and we asked them a number of questions about the technology that they use. I think it will come as no surprise to anyone that Excel comes out at the very top of the list of tools that are being used. The number of respondents who said that they use it not at all or less than once per month is de minimis. You may contrast this with other tools like MATLAB. Sorry, MATLAB is a great environment. I've used it and it's quite good, but it does not enjoy a lot of adoption. And then there in the middle, you'll see, I think, some newly emerging technologies like Power BI and Tableau, some old standbys like SAS, and others are sort of in the middle, but clearly Excel remains preeminent. Now, over the years, I've had a number of reactions about the widespread adoption of Excel. In particular, once I had my kind of Damascene moment with R and began using it on a daily basis, I really questioned why Excel enjoyed so much use. And I was very troubled by that. I've since altered how I think about that in ways that will become clear in a moment. But why did I initially have this skepticism about Excel? And why did I love R so much? There are a number of reasons, but one of the things that we need to introspect on and is useful to consider is the feature set of a particular tool. So let's consider Excel. Some might regard this as kind of anti-marketing when I say that some of the pros for Excel, it's very easy to format exhibits for printing. I can adjust font size and table structure so that I can have the information fit on an 8x10 or A4 sheet of paper. It's great at that. R or Python are not so good. Trying to get things to paginate properly and fit onto a page is a bit of a chore for scripting languages. Why else do we use Excel? I can send someone a spreadsheet. I can put it onto an email and they can receive it, they can open it up, and they can ingest it instantly without having to install R or run a script or things like that. Excel is easy to learn. That's maybe a pro and a con. We have users that can quite easily modify the techniques, but the fact that it's easy to learn means that it is very easy to engage with a wider community of users. And then finally, this is the one that I think weighs heavily in the industry, interactivity. The idea that I can change some of the assumptions and instantly I can get a result. You know, how does this affect things? So what are the cons? Very hard to lock down. We're still in a situation where I'm pretty sure if you password protect a spreadsheet, I can defeat that, right? All I do is just do a save as without the read-only protection and then just swap the name of the file. I think they might have defeated that, but I know that there was a time when password protection in workbooks was barely a speed bump for anyone that wanted to overcome that. Version control is, I'm going to say non-existent. In practical terms, it is non-existent. And the statistical support for Excel is, I'm going to say, for the modern actuary, rather weak. We've got normal distributions, maybe there's a gamma, We might have a Poisson cumulative function, but the inverse Poisson or random number generation for any non-trivial distribution simply isn't there in the kind of the factory install for Microsoft. So the statistical support is not really there. And when you get into statistical learning, predictive analytics, look elsewhere. If you need cluster analysis, decision trees, Excel is not going to support that. So scripting languages. Here I've got the Python logo, but for Python we can say R, we can say Python, we could say Julia, maybe we could say JavaScript or things like that. Very easy to lock down. I can have my code that is, perhaps in a package or some other form where the user cannot easily augment it. Version control, yes, please. I use Git routinely. Just this week, I'm working on something and making pushes up to GitHub, and we're developing something in a very, very controlled and deliberate way. In terms of the feature set, when it comes to predictive analytics or statistical learning or any sort of statistical technique, I think you would be hard pressed to find something which has not been implemented yet. And scales up very, very well. You can use the same script to run against a very, very large data set. Excel has a maximum number of rows. It's no longer 65,000, but in practical terms, I don't know that Excel scales up all that well. In terms of the cons, the learning curve is steeper, sure. So you're going to have employees who use this that maybe be a little bit older, a little bit more expensive, or if you want to change your analytics department to have them adopt a scripting tool, there's going to be an investment of time. And then finally, this interactivity, which is a very, very thorny issue. And let's talk about that. When it comes to interactivity, the reason why we can say that it is not really a feature of scripting languages like R is we need to adopt the perspective of who is ingesting the analytic work. For me, I think that R is quite interactive. I can change a parameter or hit Control Enter or Control Shift K or something like that, and I will get an output. But that's not true of the users that I'm communicating with. There are ways around this. Well, okay, perhaps we cannot give the user a scenario generator, but we can give them a kind of a table of what I would describe as sensitivity analysis. Maybe this will appease them, but it's not going to be enough. We can think about technologies like Shiny or Dash. That is a place where we're getting into kind of production software and user interface design that gets us further and further away from analysis. Now, really the problem is what I like to call and think of as the cake mix problem. So if you've read Malcolm Gladwell, this is where I got this notion, you'll know the story of the introduction of cake mixes, I think primarily in the United States, but elsewhere as well, in about the middle of the 20th century. We had figured out how to package a product that was powder, and you could add water to it and it would become cake. This sounds like a really fantastic thing, and that people would readily purchase this product and use it. As it happens, it was not a success because the people who were going to make the cake, there was not enough of themselves in the cake mix, right? They were not participating in the process all that much. Only when they changed the cake mix so that the person who was using it, they had to add eggs and they had to add oil and water and maybe something else, only then was it successful. So this is very interesting. When we make the product seemingly less efficient for the user, it becomes more successful. And that is a lot of what I think is going on with spreadsheets. Because from the perspective of the user, we have this temptation to give them cake mix that's very, very efficient. But the decision maker, I don't believe it. I can't see the ingredients. Excel is an environment where the data is visible, but the logic is hidden, right? So I need to be able to see the ingredients. And further, I won't use it until I can modify it myself. I must make it my own, right? I have to put my own stamp on it. So this is the problem. And now we have this decision, right? Is seemingly one where there is a foregone conclusion. Are we going to continue to use Excel forever? Or are we going to shift to scripting languages like R or Python? Which lane are we going to pick, one or the other? Well, ¿por qué no los dos? Why not both? This is an example of a spreadsheet that you should be able to find. It is on OneDrive, and I think that anybody with the link can look at it. I don't think that I've marked it read-only preferred, so anybody can modify it, probably. Please don't break it. But we'll send the link around at some point. But there is out there on the interwebs an Excel workbook where we're going to calculate an increased limits factor. Now, this is not a very complicated calculation. For actuaries, it is not a very complicated calculation. For an underwriter, probably it is. And we could, if we wanted to, code the logic for the ILF calculation in the workbook itself. I can pull a formula table off of the textbook for any distribution that I like, and I can calculate the limited expected value. It's not that big of a challenge. I'm doing this for illustration. And so even though I can do it manually, this has already been done. The Actuary package in R has limited expected value calculations for a wide range of loss distributions. You've got Weibull, you've got Erlang, you've got whatever features that are not in Excel. So I'd like to be able to use that existing art, that existing infrastructure. So what I've done is I said, all right, the reality is that Excel is the user interface. That is the person who needs to be able to enter values on the sheet. But I don't want to use Excel as my calculations layer. What I can do, though, is I can code that calculation in R. And I can then use this package, Plumber, to deploy it as a web API. All right, if we're not familiar with web APIs, here's what they are. API, Application Programming Interface, is very, very common. If you have done interactivity with the web at all, you are very probably engaging with a web API. Imagine that I am on my browser and I send a command to the World Wide Web. It'll be an HTTP request. The web server will absorb the request, it will process it and send a response back. All of this happens on the hypertext transfer protocol layer, the basis of the World Wide Web that's been around since about the 1990s. And it looks in a browser like this. So we're using this, in internet terms, old technology, but we are using a rather modern interface to get a result. That is a little bit difficult to read, but just to hammer home the idea that all of this is happening via HTTP communication. My laptop is communicating with a web server and I'm getting a result back. So if you can read the web address there, we are passing in parameters as elements of an HTTP request. And then there, the browser is giving back a very, very dull web page, which is the increased limits factor. This is a better way of looking at this. So I open up an account on DigitalOcean. So I could have a server. I didn't need to, nor do I know how to actually provision and deploy a web server, but it doesn't matter. DigitalOcean just handles that. And that link, again, you can click on that link and that will take you to this page that we see here, where the API has a pretty nice looking descriptive interface, and I can experiment with various parameters. I can switch what distributional assumption that I have, and I will get a response back. It's all kind of cool. We start with a spreadsheet where I can design the user interface, and I can turn that around pretty quickly. I'll be candid, I can knock together a set of inputs in an Excel workbook faster than I can write a Shiny app. It won't be all that pretty. The Shiny app will look much better and it'll be a bit more robust, but I can turn it around very quickly in Excel. I can write the actuarial logic in R or Python or JavaScript or whatever. And I can use that larger feature set in an environment that I'm very comfortable with. And then between those two layers, I've got the web server that is the kind of glue that will bind the application together. Now, from the user perspective, the person who is using the workbook, all of that back and forth is largely invisible to them. You know, we say you need to be connected to the internet, but they probably assume that. A lot of benefits. The actuarial logic does not reside in the Excel file, so it's locked down from user prevention. We've got the richer feature set. We're consuming the web API in Excel, but there's no reason why we need to be limited to that. We could design a mobile app where an underwriter could, on the fly, calculate an ILF because we are exposing it via a web API endpoint. We can version the code because we're coding it all in R. So we've got Git or SVN. We can painlessly deploy bug fixes. We don't need to fix a formula or VBA and then tell people to start using a different spreadsheet. And we can version control the API itself, right? The endpoint that they are accessing is something that we can fix as one of the inputs in the workbook. All right. So when we are thinking about the technology that we're using, think about the feature set and think about what it will take to get operational harmony. We don't necessarily need to assume I'm most comfortable with R, therefore I need everyone else to adopt, nor do we need to say that the users, look, I can only consume it in Excel. I'm not going to get the cake mix unless I can add eggs. We can think about ways to meet the needs of both sets of user communities. All right, so that's a little bit about technology. I want to talk about some of the non-tech elements of the actuarial future. Depending on who I'm talking to, the foregoing is going to scan as either really fascinating and really fun, or it may come across as obscure and wonkish and an over-engineering of a very a problem with a very straightforward solution. I can imagine, because I've worked with some people, API, I barely know how to spell that. Why are we overcomplicating this? But really, we're not talking about technology when we think about the foregoing, despite the fact that it relies on a technology stack that really didn't even exist 5 years ago, 10 years ago. We're talking about a human problem, right? This is an operational issue, not a technological one. Actuaries, for the most part, if they work at an organization of a certain size, actually, I'm going to go ahead and say most organizations, they're given Excel, which is a spork. A spork, if you've not encountered them, they're made out of plastic, they're cheap, they're disposable. It's very, very easy to give someone a spork, and you can eat almost anything with a spork. So they seem very, very practical and a very simple solution. They're effective, but they don't do enough. So when actuaries need to deliver solutions, we've taken the spork that we've been given and we've converted it into something like this, through VBA, through coding add-ins, through calling into a C runtime that someone has developed. We've taken a spork and converted it into this highly effective tool that tends to obscure the operational issues that we're dealing with. So what's really going on here, when we talk about technology, we're not necessarily talking about technology. We're talking about operational issues. We're talking about human wants and needs. So what does the future look like? It's pretty clear, I shouldn't say this, let me temper this. My assumption is that Excel's problems are unlikely to go away anytime soon. Okay, you can have 1 million rows in an Excel workbook. That doesn't mean that you should be running that much data through it. The operational risk issues, it has been a long time that they have been in existence. They continue, they're not going away anytime soon. All right, so Excel is here for the foreseeable future. It will be here because the demands of users are such that it will remain. And this is a user community that is one where the technical users of Excel are very much the minority. I think the majority of Excel users would be the kinds of users who look at a feature which says that we can sort data based on the color of the font. That is viewed as a step forward. That is viewed as a good thing. I will go on record as saying that that's a dreadful feature, that erodes the robustness of the analysis model. But I am not a typical Excel user. So we're going to continue to have this tension. If we only deploy Excel, then what we have is a very visible manifestation of a poor operating model. Now, smart organizations will recognize this. Rather than saying, this is the tool and we're going to use it forever and ever, what smart organizations will do is they'll realize that actuaries need to have a seat at the table in operational deployment. Because in the end, what we are resolving is not a technological problem, not an analytic problem, but a human one. And the human problems are only going to get more interesting, more complicated, more difficult to solve. So question, particularly in the United States, there is a lot of conversation about bias in insurance operations, bias in insurance pricing. Now, is that a human problem or is it a technological one? The answer is yes. We may think, well, this is really a human problem because if we are only looking at objective algorithms, then things like bias, this is a social issue. This is a human issue. But it's one that demands an analytic technological solution. We have models that rely on a pretty massive amount of mathematics, where we saw a really fantastic example of that in the prior talk. Looking at bias is one where we're adding a constraint to the optimization, one or more constraints to the optimization. What we're optimizing is we are optimizing insurer profitability, or we're optimizing risk capital or what have you, but we're adding an additional constraint. And that has a mathematical, technological element to it that actuaries are uniquely positioned to think about and to address. So this set of candidate definitions for equity in a model are from a paper associated with yet another R package called Fair Models. I'll confess, I had never heard of this package about a year ago. The idea of algorithmic bias was, until recently in my life, something that was an element of perhaps professional conduct, of operational decisions, marketing decisions, regulatory decisions. But it was not something that I had thought of in a mathematical way until recently, when we reached this point of consideration of the operational elements of fairness in pricing. Now, this package that I'd never heard of, I said about a year ago, I'm being a little bit overzealous there. I didn't hear about it, I think, until August of last year, when I read this paper. And I'm one of the, you will not have seen this paper. It's coming out any day now. I think middle of February, we're going to get several papers from the CAS. This is a great one: Methods for Quantifying Disparate Impact in Insurance. So the conversation has taken on a new element where we're looking at some of the social pressures that exist, and we're treating this in the way that an actuary will typically do. It's constrained optimization. It is developing mathematical methods to address what is a human problem. Right. Let's talk a little bit about scale. This is something that I think gets a lot of attention in the press. If you read trade journals, the future is big data and AI. And when I say big data and AI, I want to be clear that I'm thinking of, and I say AI, I ought not have. In the popular press, AI is what we see very often. I'm thinking of algorithms that have a high dimensional predictor space, right? I'm going to call it like 100, 200 candidate variables, and large volumes of data, right? So I say AI, but I could just as easily be saying XGBoost or random forest or what have you. So if I open up a trade publication, the future is big data and AI, but is it? I think that AI is something that deserves a great deal of attention, but it is not the only methodology that we should be thinking about, nor is it without some implications. So big data, all right, high volume data. What coverages does that speak to? What insurance coverages are we referring to there? These are going to be coverages that are pretty well defined. Those are going to be items like workers' compensation in the United States, going to be personal auto, it's going to be motor. Those coverages that have been around for decades and longer are ones that play in a very mature market. We're going to have low margins on those coverages, and we're going to have consumers that will regard the coverages as being largely commoditized. I'm not sure what the state of play in UK motor is today, but I can tell you that 15 years ago, when I was a little bit closer to that market, customers would switch for very, very low premium amounts, right? 50p, and they will switch carrier. That's tough, right? And I can say that in the United States, when I moved back here, oh gosh, over 10 years ago, and got reacquainted with commercials on television, it seems like every third ad is for a personal auto insurer. Right? I got very familiar very quickly with Geico and Allstate and Progressive and USAA. So when we talk about high volume coverages where AI and other techniques like that are going to perform well, it's the coverages with high marketing costs. Now, this isn't necessarily negative, but it does speak to a particular coverage that is not the totality of the insurance market. Here, we've got some risks that did not exist some years ago. There was a time when aviation insurance didn't exist because the airplane had only recently been invented. The same applies for satellite insurance. It was not that long after manned spaceflight and commercial flights to position satellites that we needed to insure that risk. Drones are another coverage that would not have existed, say, 10 years ago. And these are coverages where we don't have a high volume of experience. we don't have vast swaths of customers. We will. I think it's fair to say that some of these coverages are rather mature now. Cyber is one where I don't think that we're there yet, despite the fact that companies are writing rather a lot of cyber coverage. That is one where you couldn't really compare it to commercial property or things like that. So some algorithms, the ones that get a lot of the attention are ones that scale up. But we need to ask ourselves how well our analytic processes scale down. And this is one where, to me, we're not finished with parametric models, right? So yeah, AI or random forests, these are, I think, at best, kind of quasi-parametric. Parametric models, like linear models or things like that, they can scale down rather well, but more broadly, and I'll get into this in a minute, there are other techniques that lend themselves to low volumes of data. The way that I tend to think about this is with yet another baking metaphor. Whenever I think of a parametric model, I think about biscuits. And I saw on the list of participants, we've got some folks from outside of the United States or might not be familiar with the Southeastern United States. A biscuit is not a cookie. It is not a scone. It is a very savory baked good, generally for breakfast, although if you ask me, any time is a good time for a biscuit. The formula, the parameters for making biscuits are rather straightforward. I had an approach that I used for a very long time where I would measure the ingredients by volume. And so I made an operational shift and began to measure the ingredients by weight. And suddenly that operational change meant that I could scale it up or down rather easily. If it's my family and I eating, we'll make a dozen. If it is something that I'm making for some guests who are joining us, I will make 20. If I'm making them for a large group of people, I can make 50. I can make one biscuit if I want to, because the parameters are invariant. So this is something that scales up and down rather well. The actuarial equivalent is Bayes' theorem. Bayes will scale down very, very well. We bring to a Bayesian analysis, I think we're all familiar with this, ideas about what we were expecting to see in the data. And those ideas will persist even if we have a low volume of data. Now, the data will cast some influence over our preconceived ideas, but we don't automatically need large volumes of it to get going. I used drones earlier rather deliberately because at my last kind of traditional actuarial role, the company where I was working wanted to offer drone coverage. Well, we hadn't had drones, so how then do we determine a price? And I said, well, okay, how frequently do you think that the drone will crash or the operator will do this? Like, how many hours of drone flights will it take to generate a loss? And we can posit this once every 10,000 hours of flight or what have you. Okay, and what will the damages be? There we've got some notion about the general liability damages. So we've got a model. We have no data, but we do have a model. And we have a model that will automatically tweak whenever we get data in. If I had wanted to bring more parameters to bear, I could have, right? So they scale laterally rather well too. I can make a model of some stochastic complexity and I can run it without that much extra work. I'm being a little bit generous with this here, but I can say that frameworks like STAN, like BRMS, make it very, very easy to generate quite non-trivial models. And we've also got scenario sensitivity analysis. I can have two different underwriters, two different claims personnel, and I can ask them for their ideas, and I can build a model that will show the different implications of their assumptions. So
Brian, we have about 2 minutes maybe. So we
You
don't,
got it.
yeah.
So scale is a two-way street, right? We need to scale up and we need to scale down. And that brings us back to Hallie. Now, what would he say? And here I'm going to cheat a little bit and just say that I think that Hallie would recognize, if not the technology, he would recognize what it is that we're trying to do. All right. We're looking at disparate feature sets to address operational issues. We are continuing to think about human problems, whether they are an insurance company's operations or social demands for treatment of bias. And then finally, scale works two ways. Hallie could not have done the large volume data work, but one of his contemporaries, Reverend Bays, would recognize some of the low scale problems that we are trying to address. And with that, I am done. Thank you very much for your time. I will take questions if there are.
Thank you, Brian.